The next problem deals with Fourier transform. Very important part of communications, and the last of the three transforms that we have discussed. The first one was Laplace. The table is provided. We need to make sure that we understand how to go from time domain to the S domain, and using the inverse Laplace from the S domain to the time domain. Partial fraction expansion comes into play. When we are dealing with Z transform, it is essentially your Laplace in the discrete domain. And pretty much everything that happens in Laplace applies there in the same methodical manner. It's just that when you're doing the inverse Z transform, I strongly recommend students to actually divide the function by Z, and it comes in handy when you are doing the inverse Laplace transform using the tables. Fourier transform. Before we dive into this particular problem, which again is more of a problem related to sketching the triangular pulse than anything else, one key point that I want to tell you about Fourier transform is that the transform pairs, and in fact that applies to Laplace and Z as well, please listen carefully, that the transform pairs that are given to you in those tables apply individually on the functions only. For instance, if I have a function f of t, and I've tested you guys multiple times in the on-demand course and quizzes, mini exams and whatnot. If I give you a function f of t, which is sine of t, okay, and the other one is f dash of t, well, dash is probably not a good variable because it indicates a derivative. But there's another function called g of t, which is sine t dot cosine t. And I ask you to actually figure out a Fourier transform of this and a Fourier transform of this. Fourier transform of f of t should be a slam dunk because you just look up the pair in the reference handbook. Correct? What I find students doing so this is fine. What I find students doing for cases like g of t is they go ahead and apply Fourier on sine of t, a Fourier on cosine of t, and multiply them together. It is absolutely wrong. Okay, please don't make this mistake. What you need to do is trigonometric manipulation and consolidating this product of two sinusoids into one sinusoid. And there are trigonometric identities out there, double angle formulas, half angle formulas, that will allow you to do that. So this is just a side note, okay? And one of the many ways that they can trick you on Fourier, and you have several practice problems that you can see in the course resources and the study guide, homework assignments and whatnot, okay? So let's come back to this point. And student is asking about communication theory of triangular pulse. It is given total time is 2t. I'm a bit confused. So the question itself, with all due respect, is a little bit confusing question, but I've sort of paraphrased it for you and created two scenarios actually. If I look at this problem, I'm calling it problem number 6, okay? Calculate Fourier transform of a triangular pulse centered at 0 with amplitude of 4 and duration of 2. Okay, so we know that this is how a triangular pulse is defined. Okay, and 2 tau, this is from the lecture notes, is the total time period of the triangular pulse. Now here's the thing. The question says that the duration of the triangular pulse is 2. So that basically means that from here to here, it is 2. Correct? So what should be the value of tau? For triangular pulse, just like the rectangular pulse, tau itself ends up in the denominator by itself? Should it be 2 or should it be 1 or 4? Are you guys following me? So this whole thing is 2, correct? And if you pay attention, then from the standpoint of tau, it is 2 tau. So 2 tau is equal to 2. Tau should be equal to 2 by 2, which is equal to 1. And when we look at the transform pair from this point onwards, 4 triangle t divided by 2 is not equal to 4 triangle t by 1. Make sense, guys? So how you interpret the value of tau is going to impact your final answer. So let's look at this scenario. Calculate the Fourier transform of a triangular pulse centered at 0. So t minus 0 emphasizes that. And duration of 4. So when I say the duration is equal to 4, I go here, I quickly mark this up. I'm like, okay, this is 4, right? So this is 4. Now I start constructing my rectangular pulse. So this is a magnitude of 4, okay? Centered at 0, so far so good, duration of 4. So let me actually extract the value of tau. Okay, so the magnitude is 4. That's good. Centered at 0, okay? And how do I figure out the value of tau? I recognize that 2 tau is equal to 4, which means that tau is equal to 4 divided by 2, which is equal to 2. So this is correct. Because for a triangular pulse, 2 tau is equal to total duration. And then we apply the transform pair, which is given in the reference handbook. It's very easy to apply. And you end up with this. So please pay special attention to the difference in how tau is treated for a rectangular pulse versus how tau is treated for a triangular pulse. Also, when you're doing Fourier transform, it is important to recognize that Fourier transforms pairs that are provided in the reference handbook apply to individual pure functions, not the product of functions. And if you find yourself where multiple functions are being multiplied with each other, then you need to convert that into one pure function. Does it make sense? And there are plenty of practice problems in the on-demand, the live training homework assignments, quizzes, study guide for you to work through. If you're new to this channel, please consider subscribing. On a weekly basis, I'm creating content for FE electrical and PE power exam preparation. I also discuss topics related to electrical engineering with a focus on power systems engineering. If you'd like to learn more about my FE electrical and PE power exam preparation programs, please visit my website, StudyforFE.com.